Hello and welcome back to the next set of bonding news for us here in chemistry. Uh, we've talked about bond polarity. Let me just do a quick recap for that before we get into this topic. We've talked about bond polarity in the last video. And bond polarity comes from the electronegativity. Okay, so when you're dealing with two elements, element X covalently bonded to element Y, you have to take into account which element has a greater attraction for electrons. In this case, let's just say Y has a stronger pull, so we could call it a 3.0 versus a 2.0. In this example, the electrons are being pulled in this direction, causing our partial charges on the left and the right side of this bond. So the one thing I just want us to keep in mind is that in this bond idea of polarity, we are only dealing with the polarity of two atoms. Now, we still have to use this concept while we're dealing with polarity of a molecule, but then we have to, essentially what we're going to do with the polarity of a molecule is we're going to look at all the bonds. Okay? And so that is kind of what we're dealing with. Bond polarity is one specific bond, so two specific atoms, whereas molecular polarity is all of the bonds and all of the atoms. And the way we do this is we're just really looking at the shape. We're just looking at the shape. Molecules that are symmetrically shaped will be considered nonpolar molecules. And the reason is they have an even distribution of charge. So I'm going to give you a couple of examples, and hopefully you can understand what is meant by an even distribution of charge. I'll start with one of the easiest ones to see, and that would be methane. So CH4. Right, now, in this molecule, there are four bonds, and each of those four bonds have their own bond polarity. And using our reference table, we'll use the exact numbers so that we can take a look at it. Carbon is 2.6, and hydrogen is 2.2. Now, each one of these bonds possesses their own bond polarity, and the electrons are slightly pulled into the center. It's not a great difference. It's honestly classified mostly as a nonpolar bond, but it's polar enough for the purpose of this video. So the electrons are pulled slightly that way. This hydrogen is also 2.2 for its electronegativity. Each one of these, and in each one of these bonds, we have a slight pull of electrons into the center to the carbon. Now, the molecule as a whole is symmetrical, and I'm going to explain the easy way to understand that in 1 second, because there's a lot on the board here. But I'm first going to explain the deeper understanding. And the deeper understanding is that if the electrons, let's use purple, if the electrons are slightly pulled into the center from all different directions, it gives this slightly partial negative area for all of the molecules. Every one of these bonds pushes their electrons slightly in the center, which means that there is electrons missing from around the outside. And so on each of the hydrogens, there is this slightly partially positive thing. Again, we're looking at the whole picture. What I'm trying to get you to understand is that a symmetrically shaped molecule as this, what happens is I refer to it as the net location of these 4 positive charges, right? The net location, the average location. The location, let me just try it this way. If this was a graph, okay, X and Y axis, there's a lot of layers on here, but it will make sense. If this were a graph, what would the average graph position be for these 4 orange dots? The average location for these 4 orange dots would be right here. This center location is the average place to find all of the partial positives. And because this average location of positive is the same place as the average negative location, the overall molecule possesses a non-polar characteristic, right? Even though there are positives and negatives, they all negate each other because their location overall, positive and negative, are in the same location. Okay, and that's what makes this a non-polar symmetrical molecule. It's a tough concept. It really is a tough concept. It's not easy. Nobody said it was going to be easy. Now, I'm going to show you the easy way to be able to figure this out. That's the very high level, right? That would be more something like a college level or a very advanced high school course. AP chemistry would probably discuss that as well. But for Regents Chem, which is what we're trying to help all of you out with here on this channel, is you just got to kind of look at the picture. All right? You just got to kind of look at it and say, hey, if I divide this molecule right down the center, is the left side the same as the right side? Yeah. 1 hydrogen on the left, 1 hydrogen on the right. Carbon gets split down the middle. H gets split down the middle. So yeah, that is symmetrical that way and that way. If I divide it this way, is it also symmetrical? And it is. All right, and the dual symmetry helps make that happen. The one thing I want you to really keep in mind, because some people may be asking this question right now, and I don't want you to be, because you might be thinking, well, wait a second. This carbon right here in the middle, half of it has the curvy side and the other half does not have the curvy side. You can't look at the letters, folks. You can't look at the letters. You have to think about them as what they are. And what they are molecules. These are atoms. I'm using spheres. They're not necessarily spheres, right? And unfortunately, I couldn't make them the exact same size, but it's close enough, right? You have to think of them as different colored spheres, and in that case, it becomes really simple for us to see that there is symmetry in this molecule. I'll give you one more example, all right, of a non-polar molecule. It's a very famous one in that it always shows up on the regions, and that's carbon dioxide. All right, and I'm going to try and make this a little bit speedier of a conversation for the polarity thing. The electrons are pulled to the oxygen in a CO bond on both sides. Okay, so the electron density, where the density of the electron mostly is, finds its way over here and finds its way over here in that bond, leaving the carbon to have this partial positive situation. Again, I asked the question, this is the higher level understanding of it, where would be the average location of these 2 points on a graph? That average location would be right smack dab here in the center. And so if I just, instead of overlaying This time I just tried to do it underneath. If I move that right up, the positive and negative find themselves in the same location. This molecule would have to be a nonpolar molecule. All right, but for simplicity's sake, it becomes really easy for us to see when we just draw two lines down the center. Whoa. When we draw a line down the center, oh, that has symmetry left and right. We draw symmetry that way. Yep, those are nonpolar molecules. Polar molecules are the opposite, okay? These are asymmetrically shaped molecules. Okay, they have an uneven distribution of charge. There we go. Uneven distribution of charge, and this time we're looking for something that is not symmetrical. So the first and most prominent thing that the Regents does ask about is water, H2O. So in this picture of water, we can see, using our symmetrical technique, that there is symmetry left and right. Okay? But if one of these symmetrical lines is not symmetrical, that makes the whole molecule polar. And the moment we try and divide this top and bottom, we see that the symmetry line does not exist. Right? And that makes this a polar molecule. But I like the higher order thinking, and so I'm going to explain to you briefly what is it about electronegativity that makes this polar as a molecule. And so oxygen has the higher electronegativity, so the electrons get pulled in this direction in both of these bonds, leaving the overall partial negative location right up there, because that's where the electrons are pulled. I need you to go back and think about graphs and dots and lines again. And if this side of this bond is the partial positive, and this side of this bond is the partial positive, what would be our average location of here and here? And hopefully you're thinking right in the middle of them. That location would be right here. This is the average location. Very different from up here, where the average location of positive and negative was in the same spot. The average location of positive and negative are not in the same location. And this is what makes this at a higher level. This is why water is a polar molecule. So again, I'm trying to teach you both the higher level understanding, but also the basics level, so that you're able to succeed at the Regents chemistry level. Because hey, let's face it, some of us that are here and they're watching this, you're not going on to be a chemist, but you definitely want to try hard and make it through the chemistry curriculum. And so this, I hope, will help you, both of these techniques. One more example, and I'm just going to show it to you without diving too deep, is this. And I'm just going to show you with lines of symmetry. You divide this molecule right down the middle. The left side and the right side are symmetrical to one another. But we have to look X and Y. And if we divide this way, the top and bottom of this molecule are not symmetrical. And this makes this molecule, again, a polar molecule. Right? And this, here are three pictures that, we can quickly look at. We've already discussed water, but I'll show it to you again. That is a symmetrical line, but this is a non-symmetrical line. that's a polar molecule. Divide this right down the center, H on the left and F on the right. They are two different atoms. This is not a symmetrical line. This, again, is a polar molecule. In this picture, we divide it down the middle. The left side looks exactly like the right side. We divide it down the x-axis middle. The top side looks exactly like the bottom side. This picture represents a non-polar molecule. All right. So I hope that video helped you out, understanding polar and non-polar molecules. It does, at the high level, it does take us thinking about bond polarity to understand where the molecules are going, where the electrons are going. But if we want to just really look at it from the simple standpoint, we just got to draw symmetry lines. And you draw symmetry lines, you'll be able to figure out if it's asymmetrical or symmetrical. So, if you stayed long enough to watch the end of this video, you're going to be left with a little bit of a treat. There's an acronym that was given to me by a student from a long, long, long time ago about this topic. And that acronym was SNAP. And what that stood for was symmetrical is nonpolar, asymmetrical is polar. And it's just a nice little acronym. Some kids like acronyms in order to remember things. To remember, molecular polarity. And the good part about SNAP is it does also refer to bonds, right? So you could use this acronym for polarity of a molecule or polarity of a bond. Because if you have symmetrical, meaning the same electronegativities, you have a nonpolar bond. If you have symmetrical shape, you have a nonpolar molecule. You have an asymmetrical electronegativity, meaning that they're different. That's a polar bond. And if you have an asymmetrical shape, that means you have a polar molecule. So I thank you for watching this video. Please like it if it's helpful. Subscribe and leave a comment if there's anything you would like me to clarify for you. All right, thank you very much. Have a great day.